It's resolved. This video has been prepared for educational purposes only. No part of it may be reproduced or copied without the permission of the copyright holder.
Hello students, welcome to S. Chand Academy, the official YouTube channel of S. Chand Publishing. The book Mathematics for IIT-JEE Mains and Advanced by M.L. Khanna sir and videos by me, Subuh Nadeem. So the chapter which we are dealing today is matrices, and this is the chapter after determinants which we did in the previous lecture. This is the 11th chapter of volume 1. So some of the basic concepts let us revise. As we know, determinant, it has some value. Matrices, it does not have a value. Instead, it is an arrangement of elements. So matrices is denoted like a box instead of two straight lines as in the case of determinants. Row matrix, what is a row matrix? We all know, which is having only one row. What is a column matrix? Which has only one column. What is a square matrix? Number of rows is equal to number of columns. And what do you mean by order of a matrix? The m cross n matrix is called the order of a matrix that is having m rows and n columns. So in case of a square matrix, m and n are equal. M rows, n columns. So m cross n is the order of the matrix. A square matrix, m is equal to n. Row matrix, number of row is equal to 1. Column matrix, number of column is equal to 1. A square matrix, m is equal to n. Singleton matrix, that is only one element is there, like we have root 3, which is an element of the matrix. Null matrix, all the elements are 0, whatever be its order. We call it a 0 matrix also. Diagonal matrix, a matrix whose non-diagonal elements are 0. So these are the diagonal elements and the non-diagonal elements are 0, all 0. And it is a square matrix. It is a type of a square matrix. A scalar matrix. A scalar matrix is a diagonal matrix whose diagonal elements are all equal. So scalar matrix, diagonal elements are all equal and non-diagonal elements are 0. Unit matrix, diagonal elements are all equal and they are all equal to 1, non-diagonal elements are 0. Upper triangular matrix, so upper triangular matrix is a matrix whose elements below the diagonal elements are all 0, above can be any values. And if you talk about lower triangular matrices, then all the elements below the triangle, below the diagonal are, above the diagonal, all the elements are 0 and rest element can be any value. So upper triangular, lower triangle is 0, lower triangular, upper triangle is 0. Upper triangle means above the diagonal elements, lower triangle means below the diagonal elements. Equal matrix, if two matrices are equal, then their corresponding elements are also equal, and it is only possible if the order of the two matrices are same. Plus determinant of a matrix is obtained for only square matrices where number of rows and number of columns are equal. Addition and subtraction of matrices. So if we add or subtract two matrices, then their corresponding element gets added or gets subtracted. So I am revising all those concepts, I am not going into the detail. So if you add two matrices, their corresponding elements will get added, and it is only possible for conformable matrices for addition. That means number of rows and columns are same in both the matrices. Similarly, if you subtract two matrices, then these two must be a conformable matrices for subtraction. That is, number of rows and columns are same and the corresponding elements will get subtracted. Further, a scalar multiplication of matrix. It is very important because if you remember, a scalar multiplication of determinant, then a scalar quantity gets multiplied to only one row or one column. You can choose any row or any column, it depends upon you, on the situation or depending upon the question. But in case of matrix, if you are multiplying with a scalar, it gets multiplied with the whole, each element of the matrix. So K A is actually KA1, KA2, KA3, KB1, KB2, KB3, KC1, KC2, KC3. So this K is getting multiplied to all the elements. In case of determinant, the K was getting multiplied to any one row or any one column. Next we have multiplication of matrices. If we multiply two matrices, we have to keep in mind that it is always row to column. In case of determinant, we can multiply column to column, column to row, row to column, column to row, or row to row, or column to column. But here only row to column multiplication is permissible. In determinant it was so, because when you interchange row and column, the value of determinant does not change. But here when you interchange row and column, the new matrix come up, which is a transpose of the matrix. So it will have a different arrangement, earlier matrix will have a different arrangement. So that is why also AB, which is product of two matrices, is not equal to BA in general. Somewhere if it may come, but it is not a general formula. What is transpose of a matrix? If we talk about transpose of a matrix, that is A1, A2, A3, B1, B2, B3, C1, C2, C3 and its transpose, then simply rows and columns will interchange. That is A1, B1, C1, A2, B2, C2, A3, B3, C3, like this. Symmetric and skew symmetric matrix. Symmetric matrix, what are symmetric matrices? Symmetric matrix is such matrix whose non-diagonal elements are symmetric with respect to diagonal. Like A, B, C are the diagonals, D, E, F is here. So D, E, F will also be here. That means A and A transpose will come out to be same. If we talk about skew symmetric matrix, so skew symmetric matrix is such that its diagonal elements are always 0 and non-diagonal elements are mirror image with respect to with a minus sign. So we can say that A transpose is equal to minus A. And the value of determinant of a skew symmetric matrix of odd order is always 0. It is very important to note, value of determinant of skew symmetric matrix of odd order is 0. So if 3 order matrix is there and it is skew symmetric, then its determinant value will be 0. Adjoint of a matrix. So what is adjoint of a matrix? Adjoint is basically when you take the cofactors like this. If this is a matrix A1, A2, A3, B1, B2, B3, C1, C2, C3, then its adjoint will be, for A1 cofactor is B2, C3 minus B3, C2, B2, C3 minus B3, C2. For this one, minus B1, C3 minus B3, C1, and keep on writing the adjoint of all the elements. This is the adjoint of A. This is A and this is adjoint of A. That is, and its transpose of course. That is, when you take the cofactors of the elements of a matrix and put it in their corresponding places and then take its transpose, that is called the adjoint of a matrix. Inverse of a matrix, there is a formula very important for inverse of a matrix, that if it is a non-singular matrix, what is a non-singular matrix? Non-singular matrix is a matrix whose determinant is not equal to 0. So in that case, A inverse is adjoint of A by determinant of A. So if determinant of A is not equal to 0, then A inverse is adjoint of A by determinant of A, or you can also say that adjoint of A is determinant of A into A inverse. Further, there are some important rules, that is A into B inverse is B inverse into A inverse. Similarly, adjoint of AB is equal to adjoint of B into adjoint of A. Order reverses in all these. Similarly, AB transpose is equal to B transpose A transpose. So in all these cases of transpose, adjoint or inverse, if you are multiplying the matrix and you are taking this operation, then if you take the operation individually, then the order will reverse. And in case of determinant, there is no such concept. AB determinant is A determinant into B determinant or B determinant into A determinant. It is same. What are some other type of matrix? So let us discuss idempotent matrix. So idempotent matrix is a matrix whose square and that matrix is same. Involutory matrix. Involutory matrix is a matrix whose square is equal to identity matrix. Nilpotent matrix. Nilpotent matrix of index k is A to the power k is coming out to be null matrix, and the lower power of A is not null. So this is of index k. Now let us come to some of the questions here. So this is the first question from set 1, question 13b, page 509. If A and B are square matrices of size n cross n such that A square minus B square is A minus B into A plus B, then which of the following will be always true? So A square minus B square is equal to A minus B into A plus B. So A minus B into A plus B can be written as A square, that is A into A, plus A into B minus B into A minus B into B. Now we already studied that AB and BA are not equal. So A square minus B square is fine. This is A square, this is B square, plus AB minus BA. Now they are saying that this is equal to A square minus B square. So when is it possible that it is equal to A square minus B square? It is only possible if this AB minus BA is equal to 0, which implies that AB is equal to BA. So this is the condition here. In that case, this will be true, not always. So they are saying if A and B are square matrices of size n cross n such that A square minus B square is equal to A minus B into A plus B, then which of the following will be always true? So it will always true when AB is equal to BA. A is a diagonal matrix having diagonal elements d1, d2, d3. Then A to the power n is equal to. So A is a matrix like 3, d1, d2, d3, 0, 0, 0, 0, 0, 0. And then we have to find A to the power n. So first let us find A square, which is A into A. So d1, 0, 0, 0, d2, 0, 0, 0, d3. And another one is d1, 0, 0, 0, d2, 0, 0, 0, d3. So this will become, when you do the multiplication, row into column, d1 square, 0, 0, 0, d2 square, 0, 0, 0, d3 square, like this. So row into column, like this we are doing the multiplication. So we observe that the pattern is like a to the power n will come out to be d1 to the power n, d2 to the power n, d3 to the power n, 0, 0, 0, 0, 0, 0, like this. So we can say that option C is the correct option. Let us come to the next question. Show that A matrix is nilpotent of index 3. That means if you take A square, that should not be equal to 0. But if you take A cube, that should become 0. So let us see A square. A square is equal to 113, 526, minus 2, minus 1, minus 3. Getting multiplied with itself, 113, 526, minus 2, minus 1, minus 3. Now when you do the multiplication, first row with first column, 1, 5, minus 6. That will be 1, 5, 6, minus 6. That will be 0. Then first row, second column. Matrix multiplication is row to column. So 1, 2, 3, minus 3, 0. Then 3, 6, 9, minus 9, 0. Then second row, first column, 5, 10, 15, minus 12, that is 3. Okay. Second row, second column, 5 plus 4, 9, minus 6, 3. Then again 15 plus 12, that is 27, minus 18, that will be 9. Then third row, first column, minus 2, minus 5, minus 7, plus 6, minus 1. Then again minus 2, minus 2, minus 4, plus 3, minus 1. Then again minus 6, then minus 6, that is minus 12, plus 9, that is minus 3. Now again let us take A cube in here. So A cube will be 0, 0, 0, 3, 3, 9, minus 1, minus 1, minus 3. Don't take 3 as common because it is not in every element. It is not like determinant from one row. And this another one is 1, 1, 3, 5, 2, 6, minus 2, minus 1, minus 3. Now let us do the multiplication. First row, first column, it will be 0. Another one is also 0, another one is also 0. Because each element in first row is 0. Then second row, first column, 3 plus 15, 18, minus 18, 0. Fine. 3, 6, 9, minus 9, 0. Fine. 3, 3, 9, 6, 3, 18. 18, 9, 27, minus 9, 3, 27. That is also 0. Then here, third row, first column, minus 1, minus 5, minus 6, plus 6. That is 0. Then we have minus 1, minus 2, minus 3, plus 3. That is also 0. Then we have minus 3, minus 6, minus 9, plus 9. That is also 0. So yes, this is a null matrix. And A cube is coming out to be 0. That means this is a nilpotent of index 3. So let us come to the next question. Problem set 3, question number 12, page number 520. If M is a 3 cross 3 matrix where M transpose M is equal to I and det of M, that is determinant of M, is equal to 1, then prove that determinant of M minus I is equal to 0. So let us start from here, that we take M minus I transpose. Why we are doing so, it will be clear in a moment. So this will be M transpose minus I transpose, which is M transpose minus I. In addition and subtraction, transpose splits as it is given. Now this is M transpose minus, what is identity? M transpose into M. So M transpose into M, which implies this is M transpose into I minus M. So finally from here, M minus I transpose is equal to M transpose into I minus M. Now let us take determinant both the sides. So M minus I transpose determinant is equal to determinant of M transpose into determinant of I minus M. Now determinant of M transpose and determinant of M will be same, because determinant of A transpose is equal to determinant of A transpose, like this. So using this fact, this is also 1. So this implies, and similarly here also determinant of M minus I will be same as determinant of transpose of M minus I, and this is determinant of I minus M. This implies determinant of M minus I is equal to, now here you can take minus common, minus 1 into M minus I. Now minus 1 is a scalar multiplied to a matrix M minus I. This is a matrix of third order. So if you take this scalar outside, it will be common from 3 rows. So when it will come outside, it will minus 1 to the power 3. Because a scalar when multiplied to a matrix is multiplied to all the elements, and in case of a determinant, it is multiplied to only one row or only one column. So this scalar is multiplied to all the elements. Now if you are taking common out of the determinant, because finally there is a determinant, it is coming from all the rows. So minus 1 to the power of 3, M minus I determinant. So M minus I determinant here is equal to minus of M minus I determinant here, which means twice of M minus I determinant is equal to 0, which means M minus I determinant is equal to 0. So thus we have proved this. Next we have a question for a 3 cross 3 matrix A. If determinant of A is 4, then determinant of adjoint of A equals 2. So determinant of adjoint of A formula is determinant of A to the power n minus 1, where n is the order of the matrix. So adjoint of A determinant is determinant of A to the power n minus 1. So here determinant of A is 4. So this is 4, and this is 3 cross 3 matrix. So 3 to the power minus 1. Adjoint of A determinant. So this is 4 square, which is 16. So our answer is option number C. If A is equal to diagonal ABC, where these are the elements of this matrix, such that ABC is not equal to 0, that is ABC are all non-zero values, then A inverse is diagonal of 1 by A, 1 by B, 1 by C. This you have to prove. So A is equal to, it is given A, B, C, 0, 0, 0, 0, 0, 0. Now A inverse is equal to adjoint of A by determinant of A. This we know. What is the adjoint of A? So transpose of the cofactors. So B, C, this will be 0, 0, as you can see from eliminating row and column. This is 0. For B you will get AC, 0, 0, 0. For C, AB by determinant of A. So determinant of A will be ABC, and it is a non-singular matrix. That is why ABC is not equal to 0. So this is BC 0, 0, 0, AC 0, because transpose will be same, AB upon ABC. So this will be 1 by A 0, 0, 0, 1 by B 0, 0, 0, 1 by C. Proved. Let us come to the next question. Investigate for what values of lambda and mu the simultaneous equations this or this. The further question is has no solution, infinite solution, or unique solution. So let us start with unique solution. For unique solution, delta should not be equal to 0. So this is the delta. If you take its determinant 1, 2, 3, 1, 2 lambda, this should not be unique, equal to 0. So this is 2 lambda minus 6, then minus 1, lambda minus 3, So minus lambda plus 3, 1, 2 minus 2 is equal to 0. So lambda minus 3, so lambda is equal to 3. But it should not be equal to 0, so it should not be equal to 3. So this is the condition for unique solution. For no solution, at least one of delta 1, delta 2, delta 3 is non-zero. So, and delta is 0. So lambda is equal to 3, that is fine. So let us take 6, 10 mu in place of this last column. So 1, 1, 1, 1, 2, 2 and 6, 10 mu is not equal to 0. So that delta 3 is not equal to 0. So this will give you 1, 2 mu minus 20, then minus 1 mu minus 10, and then 6, 2 minus 2, 0. This is not equal to 0. So 2 mu is equal to 10. So mu is not equal to 10. So lambda is equal to 3 and mu is not equal to 10. Finally, infinite solution. So if you want to find infinite solution, then delta is also 0, which means lambda is equal to 3, and another condition is also 0, that is mu is also 10. This is how we find infinite solution. Next question, if the adjoint of a 3 cross 3 matrix P is this 1, 4, 4, 2, 1, 7, 1, 1, 3, then the possible values of the determinant of P is. So let us find the adjoint of P, its determinant. So its determinant will be 3 minus 7 minus 4, 6 minus 7 plus 4, 2 minus 1. So this is minus 4 plus 4 plus 4, which is equal to 4. Now determinant of P to the power 2 is actually determinant of adjoint of P, because P is 3 cross 3 matrix, and a few questions ago we have studied that adjoint of P determinant is determinant of P to the power n minus 1. So this is 4. This implies determinant of P is equal to plus minus 2. So A option is also correct and D option is also correct. Both are the correct options. If M be let M be a 3 cross 3 matrix satisfying M 0 1 0 minus 1 2 3, it is equal to it, M 1 minus 1 0 equal to 1 1 minus 1, and M 1 1 1 equal to 0 0 12, then the sum of the diagonal entries of M is. So let us see what is M. Let us assume. So A1, A2, A3 is the first row elements, B1, B2, B3 is the second row elements, C1, C2, C3 is the third row elements. Now M into 0 1 0. So this M into 0 1 0. So first row with the first column will give you A2. Second row with the first column will give you B2. Similarly C2. That is equal to minus 1 2 3. So you got A2 B2 C2. So now the determinant, the matrix M is A1 B1 C1 and minus 1 2 3 and A3 B3 C3. Now this M when multiplied with 1 minus 1 0. So again do the calculation. First row, first column. So A1 plus 1. Then second row, first column, B1 minus 2. Third row, first column, C1 minus 3. And this is equal to 1 1 minus 1. So from here what we are getting? From here we are getting A1 B1 C1 as equal to 0, 3 and 2, right? 0, 3 and 2. So M becomes 0, 3, 2, minus 1, 2, 3, A3, B3, C3. Now let us come to the last one, M into 1, 1, 1. So first row with the first column. So 0, minus 1, A3, minus 1 plus A3. First row with the first column, right? Then second row with the first column, 3 plus 2 plus B3, that is 5 plus B3. Then third row with the first column, 2 plus 3 plus C3, that is 5 plus C3. And this is equal to 0, 0, 12. So from here, we get the value of A3, B3, C3. So A3, B3, C3 is 1 minus 5 and 12 minus 5, 7. So M is finally equal to 0, 3, 2, minus 1, 2, 3, A3, B3, C is 3, 1 minus 5, 7. So sum of the diagonal entries of M is 0 plus 2 plus 7, which is actually 9. So these were some of the questions of matrices. That is all for the session, students. Keep working. All the best wishes. Thank you.